Okay, we got a lot to do today. Only reason why I want to talk about a couple things. So I want to show you the website of what's kind of happening for you. First off, the calendar. The calendar is always updated. So like for example, we had something that was due tomorrow and I moved it. So if you're ever unsure or you don't have quite the confidence in something, check the calendar. I will always be updating it if we ever make a change. So this is what I've done on the front of our page. Now, if you're starting to, I know. Every review session, the forums and the videos will be here. Okay, every day the lectures of what we're doing will be here. So like right now I'm recording, for example. These are every after school or review lectures that we have throughout the year for those chapters. So if you're working on something like, you know what, I don't quite understand some of these. I need to watch a couple different problems. Those are all the ones that we've had. Okay. Here's Crash Course Chemistry if you ever need to just watch something and you're not necessarily wanting to see specific equations, but just I need to get bigger picture idea. I just want to watch 10 minutes of just the bigger picture idea. Great. This guy, you can't see it on my screen, you can, but this is Science with Tyler DeWitt. He does a pretty good job, but you may not be exactly the topics. And then this last one's very specific. It's called AP Chem Exam Review, and it's some very specific notes if you're ever looking for something. So just giving you some ideas. And then down here will be any kinds of sheets that you may need in case if you lost them. I'll eventually be getting them all in there as well. So please be utilizing that as much as you can. Every night you should be working on at least part of a problem. I'm not giving you any other homework. So the things that you have are either your reactions or as we're working on these problems. So it's about the progress throughout, not just at the ending. If you have gotten a review book, you should start, they have plans. And one of the plans is within a month. They have 3 months, 2 months, 6 months, like how you could use the book wisely. I am thinking about, I got a decent amount also that I have that I could rent out as well if you wanted that. So we can talk about that later. So without further ado, what I need to do is we need to finish up our chapter 5. This has slowed us down in my overall idea because chapters 4, 5, and 6 are 3 chapters. If you do look, just quickly, I'm going to go back here for a second. We're getting that out and ready. Everything else is 2 chapters, more or less. So chapters 17 and 18. Chapters, I know it says 14 through 16, but 15 and 16 are really 1 chapter. 12 and 13. So we're only really doing 2 problems a day, and then I might be throwing out some multiple choice that day. Or I might be throwing out another problem. So realize that right now it's like, oh my gosh, is every day like this? This is going to be insane. These first couple days are just kind of nutty, okay? Last item, and then we're going to get going. I am also writing, just to help keep you organized, is those are the things that you are responsible for from the packet. So the second problems of each chapter, right? That's what you need to have done by that second time we hit the review. As I said yesterday, it needs to have a real good AP effort on each one. So if you're struggling with it, I try to do it, start working on it in the future. So now technically you have all these going to be due, but not until those dates. And it's just those problems that are second. And I will probably be stamping them because I'm not going to collect them in the beginning. You're going to put them all together. So Marco, don't lose any of these. As just the name I thought of off the top of my head. Okay, so this is where we left off. If you had first class with me yesterday versus fourth, I approached it 2 different ways. The first class, I actually approached it the way I would have done it. So what I did is I found the moles of each of these by using the pressures of those gases. And then the key, though, is that you need to recognize this, is that you need to take the idea that if I want O2, I would need 2 waters to get O2 because there's only 1 oxygen in there. That's the key thing for that for me. In CO2, I would need 1 because there's 2 O2s. This is what I did second class, but then I talked about this in second class. How I did it. The first one is that you could, so if you were in the first class, let's kind of check this out. You can actually use pressures as mole ratios, but it's weird. It's not the norm. So it's a 1-to-1 because there's 2 O2s for every 1 CO2, so there's 2 and 2. And then I need, for 1 oxygen, I need 2 waters. Regardless, that's the amount of gas that would result pressure-wise, okay? So I thought that was by far the hardest part of that. So if you struggled with that or didn't understand that, I want you to keep understanding on putting the scores on the points on each part. It's only worth 2. So even if you didn't do well on it, it was only worth 2. So as a reminder, we are writing this to the right side in that open area. If I start going through these and you are writing all within the problem and not using that open space, you may not get a stamp for it because that's not how you're going to be doing it on the exam. It's just, that's not how that works. So please understand that, like that's the point of that. Also, last thing I urge you to do, start trying to predict, maybe not today, maybe not even tomorrow, but start in your head, like right before I say the points, you're like, that seems like about a point. This seems like about 2. The more you have an idea of how much it's worth, the better off you're going to be able to approach a problem. Be like, oh, you know what, this is probably only worth 1. I'm just going to go with my hunch. Like, I feel like it would be this, but I'm really stressed out and I don't know. Well, if you know it's only 1, be amazed when you let your mind just kind of be free and you get a little relaxed on maybe a problem that you're hovering one way or the other. Usually you pick the right answer if you feel a little more comfortable about it. Here we go. Finishing up this one. On the basis of your answers above, write the balanced chemical equation for the combustion reaction. Determine the formula of the hydrocarbon. So this is what they're saying for letter D. And I want to show you the key to this. The key to this is that they said you got to use pressures. So they said that this was, this was 0.6. This was 0.8. And here's the important part. It made 1 ATM of oxygen, and you started with 0.2 of CH, of the CH compound, the hydrocarbon. So, does anybody see, because pressures can be ratios, do you see a relationship growing there? If I wanted coefficients, what do you see? How would you determine that? You always look at the highest or the lowest value? The lowest one, because if you divide everything in the lowest ones, you could get whole numbers, hopefully. So what do you see? This would be 1, right? So this would be a 5, 3, and a 4. Right. Because of that, what's my hydrocarbon? My hydrocarbon is C, so you gotta look. C3H8. That's propane. Get 1 point for balancing, 1 point for the formula. My intention is not to fly through this and you go, wow, I don't even know what happened, that didn't help. And maybe that's the feeling for this first set. We will be going slower as we get to the more complicated stuff. But it is also meant to get us back into it, so when you're working on your problem, that you have a reference and your mind started to see some of the things that we've worked on. Hunter?
So like in C, it says like you get the partial pressure, or no, wait, maybe it's B. Yeah, B, you get the partial pressure of O2, that's 1.2 ATM. And then in C, like you get the 1 ATM, like what's the difference between those two?
Because that was before it reacted.
Oh, okay.
Okay.
So the 0.1 is what reacts?
The 1. The 1 is the result of, after that was, like this is how much would produce the oxygen, like how much oxygen was present because of that.
Okay.
If that makes sense. All right, to finish up, E. And we got to get to, I want to get to one of the problems on the new packet too. Okay, you'd be amazed over the years how often somebody gives me a problem and I'm like, I don't know where I'm going with this, but I'm going to start with what I'm given and I'm going to utilize units. These are these kinds of problems sometimes. It says calculate the mass of the hydrocarbon that was combusted. So I need mass. I need grams. Well, I'm given this. Okay? You don't have any other information. The only other information you have is if you actually look at letter A, it says you have the moles of hydrocarbon. Remember, don't underestimate the things that you've already found. So if I have moles, and anybody want to remind me what molar mass, the actual unit of molar mass is? That is actually technically true, but it's grams per mole. So wait a minute, grams per mole, if I want just grams, I need moles. So if I use the answer from letter A, which is 6.09 times 10 to the negative third, let units help you out. Like, okay, wait a minute, I have moles. We're going to do another problem in a minute that also uses units. So this one's 44 grams per 1 mole. Where did I get the 44 grams from? From C3H8. You'd have to calculate it. Okay, today, eventually, guys, you are going to be working on some of this without me. Like, I'm going to say, let's work on this and we have time to calculate it all, but for right now, I want to make sure that we get through what we need to today with the break coming up. Check this out. 1 point. If you even recognize that you should have used that from letter A, it's not bad. I mean, you could have just written it down and did nothing. It says 1 point is earned for using the number of moles combusted from part A. 1 point is earned for the calculated mass. And then the last one. Okay. As the vessel cools to room temp, droplets, so here's my vessel, droplets of water, obviously an awesome picture, we'll do that. Droplets of water start to form on the inside walls of the container. Predict whether the pH of the water in the vessel is less than 7, equal to 7, or greater than 7. Explain your prediction. You have to slow down. When it just says water, you can't just be like, oh, water 7. You got to think about everything else that's present. Okay? And if you knew this or you didn't, we're going to try to continue to talk about some common reactions that you'll need to know. There's just a couple that you really need to know. So if you look at this equation, one of the big things that's produced, if water's forming, that means that it's being produced, right? What else is being produced? CO2. So if CO2 dissolves into water, okay? So if I take CO2 and I dissolve it into water, actually I'll do it like this. Anybody know what that could make? Carbonic acid. I'm putting bubbles in the water. Think about that for a second. That's like carbonation, right? Carbonation. It looks like this. Well, that's a weak acid. And what does a weak acid produce? H+, right? You're like, whoa, I had no idea. I get it. That's why we're doing this. So, first, answer the question in terms, in the framework of what it's asking. The pH will be, and I'm going to say exactly what? Less than 7. I'm not going to say it's under. So it's going to be less than 7. And then you need a little extra explanation. So don't over-explain. If you don't know what to say completely, don't say it all. I would just say less than 7 because it would produce H+, or it would produce a weak acid, or it would produce carbonic acid, something like that. You don't need to go further than that. How many points do you think this is worth? 2. Could be 2. No way it would be 3. I mean, just so far, we have very little experience, but based on some of the calculations and things like that, usually things are worth 2 or 1. 3 is tough, that's going to be a big problem. This is only worth 1. Usually short explanations would only be worth 1. You'd be lucky if it was worth 2. If it was worth 2, usually it's something little that you have to identify and then some other explanation with that. But usually it's just 1. So that's a 10-point problem. Anytime you see, so from this point forward, whenever you see on a packet that it's problem number 1, 2, or 3, they're usually bigger. They're worth more than a 4, 5, 6, or 7. Okay? All right, so that was the end of that one. Let's flip to the chapter 6. We're going to do just part of it. We're not going to do all of it. We're only going to do part of this one. Because part of it hits electro, so we're going to kind of put a pin in it, as they say. Okay, so some of this is going to be familiar because we just did a little bit of thermodynamics, which we'll talk about as we go. But here we go. Hydrogen burns in air according to the equation below. So make sure you're on the proper one. It's always the first one of the chapter when we go through these. A, calculate the standard enthalpy change for the reaction represented above. And check it out. Oh my gosh, they gave me a value. But they only gave me it of water. First off, huge hint. I love when they give me values on the problem. Because then that means I know I need to use them right then. But they only gave it of this one. Why didn't they give me the other 2? If they don't give me the other 2, does anybody know why or what it would be? What would the O2 and the H2 be? It'd be 0! Because those are pure elements. Remember, enthalpy of a pure element, there's no energy change because they're already made. You don't have to make anything. They've already been made. So, what do? It's products minus reactants, right? It's products minus reactants. So if you want to show your work, this is what it would look like. And here's the key to it. You got to make sure that you do double this one. So technically, I'm going to do it all the way. And it looks like that. That'd be my answer. So you had to double it. And that's just 1 point. We continue. Letter B, calculate the amount of heat in kilojoules. Don't underestimate units, please. That's released when I have 10 grams of oxygen or hydrogen is burned in air. All right, again, I don't know exactly where I'm going. I know this. I just figured out something that had kilojoules, and I was just given something that has grams. I'm always going to use what I'm given first. So, I have 10 grams of hydrogen. By the way, if your mind doesn't go too well, I probably need a T-chart. Whenever you're given grams, just about every time, you probably are putting it in a T-chart, and you're probably converting your grams to moles. So, I'm going to guess that's what I'm doing. So, I only have one data piece. Now the answer key, actually, it's interesting, they didn't use what I'm about to use. I'm going to use the value that I have. This reaction produces that amount of energy, that amount of heat, if you will. So, I'm going to put that there. Now, I'm not going to put a negative. Now, if I did, it's not a huge deal. Why don't I need to put a negative? If you read the problem, it says the amount of heat that is released. It's not like, hey, how much did you lose in the stock market? Oh, I lost negative 15,000. You just say, I lost 15,000. Hopefully you wouldn't say that at all. But if you said I lost negative 15,000, you're like, so did you gain it then? So, here's the trick. This value, the thing I want you to take from this today, is this amount reflects this equation exactly. So for 571.6 kilojoules, how many moles of hydrogen are involved? 2. Well, then why didn't you just write the 1? Well, I could have, but I'm doing it in terms of hydrogen. So let me be very clear. If this was an oxygen problem, I would have had 10 grams of oxygen. I'd have 32 grams here. I'd have the 571.6 here. And what would be on the bottom for this one, for oxygen? A 1. Because 1 mole creates that much heat. So 2 moles makes that much energy, 1 mole of oxygen makes that much energy, and 2 moles of water result in that much energy. So if I ask, like, how much energy results from having 6 moles of water produced? It'd be 3 times that, right? Okay. Well, why not 6? Well, because it's already been doubled. So that's how that would look, and I really do think we should be able to do that. We're going to do this in scientific notation. If you didn't, it's okay. This is actually worth 2 points, which I'm a little surprised. 1 point is just for the overall T-chart, and then 1 point is earned. So did you recognize that you need to kind of convert? Okay, so letter C is not a hard problem, but people make it hard. People make this really difficult. It says, given the molar enthalpy of vaporization for liquid water, H2O liquid, is 44 grams per mole at that temp, what is the standard enthalpy change for the reaction here? Okay, so I have found, I don't know why, AP students have the hardest time recognizing that they need to do this thing for problems when afterwards you're like, oh my gosh, that's all I have to do? It's always so easy for you, but you don't, it's so difficult to recognize it. If you're given a reaction ever, and you've been doing enthalpies, and you look at the reaction, you're like, man, I feel like I've been doing this already, or that's really similar. Slow down and take a look. What's different from here, from the beginning to there? It's a little different, right? Liquid to gas. Sometimes it's a compound, sometimes it's a state, but you're like, wow, that's really close. Yeah, it's really close. So what's going on is we're making a new equation. This is what makes this problem hard. That right here does not give you the equation. That equation is this, and I would write this down. It's an L. That's the vaporization of water, correct? I got vaporization of water. That's the energy that it's associated with. So I have two equations that link with an enthalpy. So let's take a look at that for a second. If I bring this up here, excuse me, can I just cross this out right now? Hey, sweet.
No.
No, what do I need to do?
You know, you double that one?
I need to double this one. So if I double that, now they can cross out. Well, what am I doing? If I put those together, that makes the third equation. That is called Hess's law. And I'm amazed how difficult it is to recognize it from time to time. And maybe they hide it a little bit, but what you need to do is say, wait a minute, they gave me an initial equation with an enthalpy, they gave me another one, and then now they're asking for a new equation. I gotta put these together. So quick reminder on this stuff. If I flip an equation, I flip the sign, right, of my enthalpy. If I double an equation, I double the enthalpy. If I cut the equation in half, I cut the enthalpy in half. Whatever it's gonna be. So in this case, just because I don't have any room, this one got double, or the top one's good to go. So I have negative, sorry, I have that. Right? And then I have the other one, and I'm going to write it like this. Get rid of that. And I add those together. So my final answer is going to be negative 483.6 kilojoules. Why didn't you use the negative 285.8? Because that reflects 1 mole. Enthalpy of formation is always making one of them, making one thing. So that's why I use the value. And that's another thing. You're going to have doubt, like, I don't know which one I'm supposed to do. After all that, though, guys, it's only worth a point. So if you didn't quite get that right, or you didn't recognize it, it's just a point. Hess's law usually doesn't have more than that. Bless you. Okay, we're going to do 2 more, and then we're going to pause this problem. We're just going to get started with it. And I need to reevaluate how I have these, because this is too tight for me to write. But we'll figure it out. Okay. Write the overall equation for the cell reaction here. So it says a fuel cell is an electrochemical cell that converts a chemical energy stored in a fuel into electrical energy. A cell that uses H2 as a fuel can be constructed based on following half reaction. Can anybody tell me when you're doing redox and you're given these equations, what's the like how, when I put these together, what do I have to make sure is occurring? Electrons on the opposite, and they're the same amount of electrons. You cannot gain or lose more or less. You got to gain, the one that's going to lose it's got to throw out the certain number of electrons. The other reaction has to take those in. So it's all about these two. So how do you know which one's on which side? You can't be like, oh, I'm just going to flip one. Let's have a little reminder on this. You look at the voltage, you want to max out your voltage. A cell is going to have the largest voltage possible. So you want to max out your voltage. You want to max forward your voltage. So which one do I have to flip? The top or the bottom? The bottom. If I flip the top, reminder, I flip, the sign flips. Be careful. Hess's law is not this. This is not Hess's law. Flipping is great, but with voltage, doubling or cutting things in half does not alter the voltage. The only thing we can do to voltage is the sign for voltage. Okay? So, we're going to flip this one. Okay? So, what do I need to do? I need to flip this. I'm just going to write this underneath, just this one. And you have the ability to write on the side here. And what do I need to do to it? There's one thing I need to do to this one. Double. Why? Because of the electrons, right? Okay. So I add it all up. This is kind of, oh, I find it funny. They throw all that out there, and then this is the equation that you get. You're like, no, that's not. Look. If you start crossing everything off, 4OH, 4OH, all that stuff's gone. All that's left is hydrogen plus oxygen gives you water. 1 point. Just 1 point. I would have thought that would have been worth more. I would have been thought that if you flipped it, and then if you got it right. That's just me. So then, we're going to end on this one for today, on this part problem. Calculate the standard potential of the cell. So all you have to do, if you have to show your work, it'd be 0.4 voltage plus positive 0.83. Yeah, I need the, oh yeah, the one that was next to it, yep. Sorry, I didn't get the label that one. So I got 1.23. And we guess that's just the point. Yep, just 1 point. Okay, so we're going to stop there. If you want to just put a little bracket, we will go back to that because that's total electrochem. We'll talk about it. We would definitely will, but I got to get to a couple other things here. So what we're going to do, we're not going to finish the other packet today, but I want to do the first chapter 7. I think you're going to like that one a lot more. So if you're like, wow, getting overwhelmed, step by step, baby steps. So if you could, get to chapter 7, please. Normally, this is the kind of a problem that I actually would send you off and go, hey, 7, 10 minutes, go. Work with someone else. Come back, let's see what you got. But I just want to kind of get this out here and show you the kinds of styles of problems. And this is a totally different kind of style. This is one that you should really take in and want to do. So let's get into it. This is atomic structure. This is chapter 7. Again, realize chapter 7, 8, 9, 8, 9 are one chapter. So I'm going to do the first 7, and I'm going to do the first 8. So you just have to do the second 7 and the 9. That's all you're going to have to do. And I, again, have it all on the board. The things you'll have to do. Okay, so we will do the other 8, or the first 8 and the second, tomorrow. It's short. Suppose that a stable element with atomic number 19, symbol Q, has been discovered. Dun, dun, dun. Hey, write the ground state electron configuration for Q, showing only the valence shell electrons. Okay, so let's talk about that. So you look at the periodic table. If you're looking for Q, you're going to be, it's going to take a lot of time off your test. It says suppose. Let's just go off of that right there. Like, oh my gosh, they did. When did this happen? Where is that? Where's it going to be? Under, to the left, to the right? Where, under?
Or bottom. Wait, no. What do you guys need? I'll be here for the row 8.
So below francium? Okay. So let's talk about outer electron configurations. I only want valence shell, so that means only on that row. So it's on the 8th row, so that's the 8th energy level, correct? What letter does that get? S, and what? How many electrons? 1. So it'd be 8s1. Make sense? I hope. Okay, that's worth a point. Just 1. Oh my gosh, turn the red. There you go. Would Q be a metal or non-metal? What I do not like about these kinds of problems, it says explain in terms of electron configuration. You're like, what? Like, I was good until it said that. So let's first just say metal or non-metal. Hope we have this right. Metal. Definitely, my gosh. It's got to be metal. Now, this is what I would say. Be specific. What I would say, it's a metal because all, what kind of metal is it? I'd say all alkaline metals have an electron configuration of, what are you going to say? S1. If you say that, it's good to go. Now, I do not like their explanation. They said all metals hold their electrons loosely. Like that has, you need extra knowledge and conversation about the nucleus and, 1 point is earned for the correct answer and explanation, which must include reference to the valence electron. So it would be a metal or an alkaline metal. The valence electron would be held only loosely. Well, I think it is more than acceptable to say metal, and then I'd say all alkaline metals have an S1 configuration. That's what I would say. So that is a point. Okay? On the basis of the periodic trends, would Q have the largest atomic radius in its group, or would it have the smallest? Explains in terms of electron structure. Let me be very clear on electron structure. Electron structure is probably things like the nucleus, or energy levels, or electrons, or protons, things like that. So first, largest or smallest? Largest. Okay, so what do we got to talk about when we talk about largest? Anybody? I don't want to give it away yet. I've already given you options. What?
Nuclear weight.
Nuclear weight, so nuclear charge or nuclear weight, like the mass of the nucleus? Nuclear charge, okay. We talk about nuclear charge. I'm glad you said that, Hunter. Nuclear charge sucks things in. You are right. It would be the largest nuclear charge, like it would have the most protons. The problem is you're contradicting your conversation because nuclear charge would suck things in. So whenever you want it to be larger, you can't talk about the nuclear charge. You need to talk about the shells or the energy levels. So this would be the largest, because and be specific, it would have how many? It would have 8 energy levels or 8 shells. I'm just going to do this for now. I'll read what they have. It would have 8 energy levels. You guys get what? So as you go across the table, you're staying at the same energy level, and it gets sucked in because you're adding protons, so it's getting sucked in. It's not getting further away. When you jump down, it balloons out because you get further away, and then you have extra shielding that occurs. This is their exact definition, or their explanation. It would have the largest atomic radius in its group because its valence electron is in the higher principal shell. You don't have to say principal shell. It's a very technical term. 1 point is earned for the correct number or answer and explanation. The size must refer to the number of electron shells. You don't have to say the number, but you need to say that it has the most. I think you should say it. They didn't say it. D, so that's a point. All these things are basically a point, except one of them coming up. You should get this. What would be the most likely charge of Q? Ion in stable ionic compound. Then again, if you're like, I don't understand what it's all saying, it's asking for the ion. It's minus? All alkali metals are +1. Does it say explain? Does it say justify? No. So don't. But please, when it does, don't just like, no, I choose not to today. Justify your answer. I'll pass. Don't do it. E, write a balanced equation that would represent the reaction of Q with water. Okay. So you just got to make sure you get this right. So here we go. Q plus water. It would be smart to do HOH. Personally. So what happens? If you do H2O, you won't get this right. You won't. It'll look like this. And now you start seeing it, and you're like, oh, well, H is kicked out, and Q goes in, and next thing you know, you have this, and you have this. And I'm not even crossing or adding things, but already that's wrong. But if you have it like this, water behaves like that. Water breaks off into H's and OH's. So Q goes in, what comes out? Yep, and what comes out of this? H comes out, Q goes in. Careful now, whenever something's by itself, gotta ask if it's diatomic. There are 7 of them. This is one of them. Now, the answer key technically has these as ions, but they didn't say the net ionic equation, so I think this is actually legit. It says the balanced chemical equation. So, view this. You may not think this one's tricky, but if you try to balance it with all the H's, it actually will take you more time. I just look at it as this is an H. That's not an H. That's no H. So this is an H. There's 2. There's only 1. Now I have 2 OH's for the 2. Oh. Check this out. You get 1 point for saying that H2 was created. 1 point is earned for H2 as a product. 1 point is earned for balancing. So just in general. Okay? Last 2. And I am shocked at this one. I must be mean. It says write the formula for the compound formed between Q and the carbonate ion, and they give you the carbonate ion. I would never do that. I would never give you the charge. They just bailed you out completely. So you look at the charge of what you gave. So what's it going to be? Q2CO3, done. That's a point. I would at least make you know that carbonate was a 2 minus. Check it out. You get a point earned as long as you're consistent with the charge you gave in letter D. So if you said Q was a 2, then it's QCO3. Whatever you had, you'd be right as long as you used it. Double I. Predict whether or not the compound will be soluble in water. Explain your reasoning. By the way, yeah, that was a point, and this next one will just be 1 point. What? It won't be? It will be. Because it's an alkali metal. That's it. Done. Soluble. One point. Right? All alkali metals are soluble. Done. By the way, if it wasn't an alkali metal, usually slightly soluble, probably not. Carbonates are not. They're hard to dissolve if it's not with an alkali metal. So that's how we do that. Okay? So what we're going to do is we are, for the rest of the hour, we're going to go through a little bit of our practice test that we took. We're not going to get through it all. So we'll talk about that.